Good afternoon, everyone. We'll wait for a couple of minutes before starting, just in case some people are joining later. Thank you for joining us. Okay, I think we can start, and if people join later, they'll just join. So welcome everyone to the first workshop organized by the STOR-HY project. My name is Marta Rodriguez, and I'll be guiding you through today's session. Our speakers, which I will introduce shortly after, will answer questions at the end of the session. Please use the Q&A function to submit your questions. So, as Europe accelerates its transition to clean energy, pumped storage hydropower is becoming more important for system flexibility, stability, and resilience. But to meet the needs of tomorrow's renewables powered and climate-sensitive energy systems, hydropower must evolve, technically, economically, environmentally, and socially. Our goal is to show how STOR-HY is helping shape the next generation of pumped storage hydropower, ensuring it aligns with Europe's climate goals, regulatory frameworks, environmental stewardship, and societal expectations. So, as you can see here, we have the agenda. Today's workshop will explore these topics with insights from experts from INUSTEC, the University of Twente, and the Norwegian Research Center, NORS. They will present the updated STOR-HY Matrix, a multidimensional tool that defines new technical requirements for ancillary services, and discuss critical factors across 3 dimensions: techno-economic, regulatory, environmental, and societal. Joining us today are Fernando Ribeiro and Sofia Barotto from INUSTEC, who will discuss the techno-economic regulatory dimension. This dimension explores the capability of the plants to provide flexibility and grid services in the current European regulatory and market framework for ancillary services. SOPI from the University of Twente, who will cover the environmental and economic dimension. This dimension assesses the environmental and long-term economic impact of plants throughout their entire lifetime, including commissioning, operation, and decommissioning. And then Jason Deegan from NORS, who will present on social acceptance. This dimension evaluates the level of approval or opposition of local communities and stakeholders towards the plans and proposed technological solutions. I'll now invite each of you to briefly introduce yourselves to our audience. Thank you.
So, hello everyone. I will be the first presenter. So, Fernando Ribeiro from INUSTEC. I have just recently completed my PhD and I work on multi-energy systems here in the research group.
Hello everyone, I am Sofia Varotto. I am a PhD student also working in EnergyTech as Fernando. And my main research topics are renewable integration, particularly offshore renewables, but I also am particularly interested in energy storage, and that's what led me to STOR-HY.
Hello, everyone. My name is Sophie, and I am a PhD candidate at the University of Twente in the Netherlands. Today, I will present environmental and economic dimensions, which is a part of our PhD research on behalf of our team at the University of Twente.
Perfect. I'm Jason Deegan. I'm based in Norse's office in Stavanger in the southwest of Norway. I completed my PhD in 2023 here in the university in Stavanger. I'm again representing two of my other colleagues who are not here today as part of the innovation and industry team at Norse. And I'm generally quite interested in social acceptance, but also economic geography and how activities concentrate in space.
Thank you very much. We're very happy to have you on board. And now we can move on with the presentation. So I leave the floor to Fernando.
Perfect. Just take control. Yeah, okay. So in EnergyTech, we'll present the techno-economic regulatory dimension. So first I will start defining flexibility, and then how is this flexibility translated as requirements by transmission system operators, so the so-called ancillary services. And then my colleague Sofia will assess the current capabilities of the demonstrators of the STOR-HY project regarding these requirements. So flexibility, it's a really hot topic discussed in power systems. It's a bit loosely defined, so we brought here three different definitions. So the first one from the regulator side. So it's the capacity of the electricity system to respond to changes that may affect the balance of supply and demand at all times. So the second one from the IEA, all relevant characteristics of a power system that facilitates the reliable and cost-effective management of variability and uncertainty in both supply and demand. And the third definition that I prefer, which is a bit wider. So it is the capability of a power system to cope with the variability and uncertainty that variable renewable energy generation introduces into the system in different time scales, from the very short to the long term, avoiding curtailment of VRE and reliably supplying all the demanded energy to customers. I prefer this definition because when we are transitioning to a system that is massively penetrated by variable renewable energy, this will actually lead the need for flexibility in the future power system. So, okay, so flexibility can be used in many different ways. Okay, so the first one is power. So, oh my God. Sorry. So the first one is power, balancing and frequency regulation. So as you know, frequency is a system-wide measurement. So, sorry. I don't know what is happening. Sorry. So power is used on the short-term balancing of the power system, basically balancing supply and demand. If we talk about the second topic, which is energy, so this is medium to long-term system adequacy and resource scheduling. So this can range from hours to multiple years. So it's a completely different approach of flexibility from power. Then flexibility can also be used for power transfer capacity, for congestion management, and it ranges from minutes to hours. And finally, there is also the possibility of using flexibility for voltage stability, which is a very important topic, as in Portugal and Spain there was a blackout a few months ago, related to this topic, which is reactive power control, and flexibility can be used for enhancing voltage stability, and this ranges from few minutes to tens of minutes. I'm sorry that this is not working properly to change the slide. Okay, so ancillary services, we are looking at this from the continental Europe perspective, since the STOR-HY project has demonstrators in Europe. So according to the existing European Union regulation, the System Operation Guideline and Requirement for Generation and Generators, ancillary services are broadly classified into categories, which are active power and voltage and reactive power. So the active power is basically in terms of requirements that are already existing for the TSOs. This is loosely the load frequency control, which is a sequential reserves that I'm going to talk into more detail here. And then there is the management of reactive power to maintain the stable voltage profiles. And we will go into detail in this now. So this graphic is well known. So the load frequency control process is a hierarchical mode of control that begins when there is an imbalance in the system. So the whole interconnected area reacts using the frequency containment reserve. And then subsequently, this reserve is substituted sequentially by the frequency restoration reserves, and then the replacement reserves. And the FRR and RR are must be maintained by each TSO, whereas the FCR, each TSO shares the responsibility, but whenever there is an imbalance, this is shared by all of the TSOs. So again, the FCR has the objective to contain the frequency immediately after an imbalance, and this is ensured by local controllers in each of the power plants that participates in the FCR. And what needs to be ensured is that in less than 30 seconds, there is a full activation of this reserve. And this needs to ensure values for transient frequency must not go below 0.8 Hertz, and the steady state frequency must not go below 0.2 Hertz. So this is how it is dimensioned. And this is relevant because each of the power plants share a burden of this reserve. So in terms of technical requirement by the European TSOs, the frequency containment reserve is basically designed to ensure that there is a reserve of 3 gigawatt, which is the reference incident or the loss of the 2 biggest power plants in continental Europe. Then we have the frequency restoration reserve, which has the duty to control to restore the frequency to two objectives. So it's to restore the frequency values to the 50 Hertz and to ensure that the active power balance between the different control areas, so meaning the import-export, need to be as it was established before the incident, let's say. So the area control error is a linear combination of these two measurements, the frequency deviation and the active power deviation from the interconnection flows. Yeah, and then the frequency restoration reserve is divided into two different requirements. So the automatic frequency restoration reserve is activated, as the name says, automatically. So by a signal dispatched by the TSO to each of the power plants that is participating in this reserve, and the plants must respond in less than 30 seconds. They must ramp up and down the power, and the other requirement by the TSO is that the time to restore frequency is 15 minutes, meaning the full activation time of the reserve has to be less than 15 minutes. And then we have the manual frequency restoration reserve, which is manually activated by the TSO. So this is not an automatic signal generated by a control dispositive. So this is manually activated. And in fact, the time to restore frequency is also 15 minutes, but this is sequential. So when the AFRR is not enough, the TSO activates the manual frequency restoration reserve remotely. And then finally, there is the replacement reserve, which gradually replaces the previous layer of control. And this is for longer time horizons. So the time frame is ranging from 15 minutes to 1 hour after the initial disturbance. So again, as you can see, we have fast reserves from 30 until 30 seconds. We have one type of reserve, then we have another, and then we have another. So there are different requirements. I will not go into detail into all of them. This has been harmonized in Europe, and I will show you the existing initiatives afterwards. So now, different topic, voltage and reactive power. This is a combination of manual and automatic controls, okay? The objective for this is to ensure that voltage levels and reactive power flows are acceptable for the TSO. And basically, the requirements that are in place nowadays are set by the requirement for generators. And basically, in the European law, there is as you can see in this figure, an outer and an inner envelope, and then each TSO will design its own envelope to be in place for each country. But basically, this means that the TSO can guarantee that a power plant that participates in voltage reactive power control can either be absorbing reactive power or injecting reactive power to ensure that the voltage level is acceptable for the TSOs. Then we have something which is not yet in the continental Europe, an ancillary service, which is the so-called synchronous inertia. So basically, this is a physical property of rotating machines that allows them to store kinetic energy and inject in the power system whenever there is an imbalance. They have a fundamental role in stabilizing the frequency after this active power imbalance. And the fact is that replacing the conventional power plants with renewable energy is decreasing the synchronous inertia in the power system. So maybe in the future, this will evolve as an ancillary service, such as what is happening in Ireland now, in which there are minimum for the dispatch, there are minimum of inertia, and maybe there will be a remunerated service in the future. So far, it is not the case in continental Europe. So synthetic inertia. The fact is that renewable generation is interfaced with power electronics to the grid, and although they do not contribute with the kinetic energy for the synchronous inertia, they can provide synthetic inertia, which is a controlled active power response, typically proportional to the derivative of the frequency, and this can be actually used as a faster way than the frequency containment reserve. So on the one hand, they do not ensure the inertia provision that is instantly provided when there is an imbalance. On the other hand, they can provide a service that is faster than the fastest service that exists nowadays. So this is relevant because also some pumped storage plants can be interfaced with power electronics, and they can provide synthetic inertia. The fact is that this relies on an instantaneous real-time measurement of the frequency, so this will never be as fast as synchronous inertia. So there is a delay, but in fact, in the future, this will be used as an ancillary service. Alternatively, there is fast frequency response, which is normally a step response for active power, so this is also faster than the frequency containment reserve, but this will not respond proportionally to the rate of change of frequency. So this will be a step response of active power. This already exists in some markets, such as the Nordics and the UK, Ireland, Australia. And although this is not implemented in the continental Europe yet, and it's not planned for the medium term as far as we are concerned, but maybe in the future this will be an ancillary service, and we are considering it in the STOR-HY project. So then there is Black Start. So Black Start, again, there was a blackout in Portugal and Spain some months ago, 3 months ago, and this was very discussed afterwards, because Black Start is the capability of the power system to restart the operation after a blackout. So starting from completely de-energized state and slowly re-energizing parts of the grid. So Black Start units, they need to be able to operate independently without any being supplied by the grid. So they are the ones energizing the grid. And so the power plants that have this capability, they must be able to operate in island mode and with very wide frequency oscillations and so on. So hydropower units are candidates. So this is the case of Portugal. So they are candidates for a Black Start. And then what I will show you from now on is that European Union has very ambitious objectives of integrating all these markets that I've been talking about, and basically harmonizing all these products all over Europe, so that the main objective would be to integrate all these markets into a single market all over Europe, to ensure market efficiency and market liquidity and so on. So I will start. This will be just a brief overview. In the deliverable that we finished just now, there will be lots of detail. So basically, for the FCR, frequency containment reserve, already 50% of the needs for the continental Europe are already integrated in a single market platform. 9 countries are participating. This is a symmetric product, meaning upwards and downwards reserve need to be provided in the same power range. The duration of this product is 4 hours. There is minimum and maximum bit size, and each country has to provide minimum and maximum. This is due to the fact that ensures no free riding and no constraints in terms of power transfer capacity and so on. Then we have the Picasso, which is for a platform for the automatic frequency restoration reserve. Okay, so the activation in real time, ensuring the low cost of the activation of the energy for the automatic frequency restoration reserve. As you can see, it's already quite integrated. Some of the members are non-operational and some are observing, but this is progressing quite fast to the full integration of the European market. And then there is the International Grid Control Cooperation. Although this is also for the automatic frequency restoration reserve, the philosophy here is a bit different, because this is addressing the imbalance netting. And what does this mean? This means that a country that is interconnected to the neighbor country, that they are not activating reserves in different directions. So one upward reserve and the next country operating a downward reserve. So this includes a control loop that will minimize the amount of activated energy. This is quite interesting. As you can see, it's already well developed and well integrated. And then there is MARI, which is for the manual frequency restoration reserve. This has been operational for 3 years already. And then there is the TECH, which is for replacement reserves, has a bit less of integration. That's it. So I will pass the word to my colleague Sofia to proceed with the demonstrators.
Okay, so hello everyone. I will now present to you the flexibility matrix field with the ranking of the ancillary services that Fernando just explained. But before doing so, I will introduce to you the demonstrators that will be involved in the STOR-HY project to assess the different aspects in terms of flexibility, but also environmental and social dimensions. So let's start with the first demonstrator that is located in France. It is called Vauglans-Saumurtier-Coiselet. And it is composed by 3 reservoirs in cascade. One of them has a very low head. And in STOR-HY, there will be an optimization of the tandem pumping scheme to increase flexibility, but also some environmental aspects. The second demonstrator, okay, it's not going. Okay, so the second demonstrator is still located in France. It's Les Cheylas, so still in the Alpine region. And it is a pumped storage system that is characterized by a high level of sediments and an intense cycling of pump turbine mode. So some improvements will regard the fast mode change to reduce the wear and tear in this intense cycling of pump and turbine, and some adaptations to more flexible market participation. The third and last French demonstrator is La Rance, which is a tidal type power plant located in the estuary of the river La Rance. And it is for this reason operated in salt water, which brings some challenges that we will see further on. And in STOR-HY, some adaptation for this saltwater condition and the problems that it can bring will be explored, and also some adaptations to more flexible market participation. Then moving to Portugal, the fourth demonstrator is Alqueva, which is the first European hybrid, triple hybrid pump storage plant, composed also of battery energy storage system and floating photovoltaics in the reservoir of the hydropower plants. And in STOR-HY, there will be the development of an optimal management system for fully exploring the benefits that can stem from this triple hybridization. Then still in Portugal, we have Vilarinho das Furnas, which is composed by a multi-stage pump that is currently not regulated. So in STOR-HY, there will be some low capex retrofitting in order to enhance the flexibility of the pump operation through the operation of the main inlet valve. And then moving to Spain, the last demonstrator, which is actually still in construction, it is a pump storage system built in an old coal mine. So the challenge that this plant has to face is that it operates with a dense fluid due to the previous utilization of this site. And these challenges will be, let's say, tackled through with some improvements proposed in the STOR-HY project. So let's see them a bit more into detail. The first one is Vauglans-Saumurtier-Coiselet. These are the 3 names of the 3 reservoirs. In these pictures, you can see on the very top the first reservoirs, and in the bottom the last one, and in the middle there is Saumurtier. So it is located in the Ain River. Currently, there are pumps and turbines installed in the first, between the first and second reservoir, and just a turbine between the second and third reservoir, so Saumurtier-Coiselet. But within the project STOR-HY, a pump will be installed also in the second section. And an innovative management system for the optimal operation of this tandem pumping scheme between these 3 reservoirs will be developed. The aims will be there will be the interest in increasing the flexibility of the plant by also increasing the total storage capacity, now having 1 more reservoir to store. And also an eye will be kept open on the prioritization of biodiversity through the smoothing of hydropicking that can have some negative effects on biodiversity, on the local fauna that lives in this river. So the second one, Les Cheylas, is a pump storage scheme located in the Isère Valley with a relatively high head and 500 megawatt of Francis pump turbines. It is, as we said, characterized by harsh fluid, so with a high level of sediments and a high pump turbine cycling. So the 2 main objectives in STOR-HY will be to enhance flexibility by also to enable faster response to the market, and to minimize the start and stop cycle through the development on innovative mode changes through a fast dewatering scheme. Then the wear and tear impact of these fast mode changes will be assessed, and also the transfer of sediments between the upper reservoir and the downward reservoir that could have some environmental benefits will be considered, but also the possible effects on the overall efficiency that could be, let's say, decreased by this addition of transfer of sediments. Moving to Larance, the tidal power plant, it is located in an estuary, as you can see from this picture, and so the head is very low because it depends on the water level difference created by tides. It is composed by 24 bowl turbines of lower power. The challenges that this plant presents are mostly related to salt water. So the first one is corrosion of the mechanical components that need to be maintained and also probably replaced more often than a plant operating in the not salt water, so in a river. And mussel fouling, so the possible growth of bioorganisms on the mechanical components that can also hinder the efficiency and that needs to be removed periodically. And another thing that hinders the flexibility of this plant is the fact that the electricity generation is strongly dependent on the tide schedule, so it is not easily adaptable to market signals, let's say. So first of all, in STOR-HY, corrosion-resistant materials will be studied and compared to consider which one is the most beneficial for such plant. And also an anti-fouling coating combined with robotized scrubbing to solve the mussel fouling problem will be analyzed. And on the flexibility side, the hybridization with a battery will be considered to make the plant more flexible and more responsive to market signals. Then moving to Portugal, Alqueva is currently located in the Guadiana River. It is a 520 megawatt plant with also pumping capability, and it is currently operating with many start and stop cycles. And what is unconventional about this plant is that it's the first triple hybrid hydropower plant in Europe. So it is also provided with 1 megawatt and 2 megawatt hour lithium-ion battery energy storage system and 5 megawatt of floating photovoltaics, as you can see in this picture, which are literally floating in the reservoir. So the objective for STOR-HY will be to explore to the fullest the possible benefits from this triple hybridization. So both in terms of flexibility and in terms of wear and tear. So first of all, there will be the development of an innovative energy management tool to also enable the participation of this plant in ancillary services market or improve the current participation in these markets. And also to minimize the wear and tear of the hydro machinery. So the fact that the battery can be combined with the hydro energy generation from hydropower plant can reduce the wear and tear due to fast power changes in the hydro machinery. Okay, finally, also there will be some battery sizing studies aiming at maximizing benefits of this operation. So it will be considered to enhance the capacity of the current battery energy storage system. Okay. Sorry. Okay. So Vilarinho das Furnas is located in the Homer River in the north of Portugal. It has a relatively high head of 390 meters. It is currently composed of a multi-stage pump and a Francis turbine. And the flexibility enhancement during STOR-HY will be to regulate the operation of the pump mode and the turbine mode with the operation of the main inlet valve, so without using variable speed solutions, but just operating the inlet valve. And for this reason, there will be the need of assessing what is the impact of the inlet valve, so in terms of wear and tear. And for this reason, fatigue models will be developed for this valve and an advanced valve control algorithm to minimize the wear and tear. Finally, Pozo Figueiredo, which is currently located in a coal mine, as you can see from this picture. It's a pioneering scheme to reconvert an old coal mine into a pumped storage system. It is composed by 3 mine pit reservoirs with 2 different heads, and 1 pump and 1 turbine of 100 kilowatt each. The harsh operating condition that characterizes this plant is the dense fluid that needs to be pumped and turbined in this plant. And for this reason in STOR-HY, there will first be attention to the plant commissioning that is currently being constructed. And then the hybridization also with a battery energy storage system and just photovoltaic system will be considered, and an energy management system for this combination will be developed. So now let's move on to the flexibility matrix, which, as you can see, it's defined as preliminary version because this is the very beginning of this project. So I will present to you the structure of the matrix and the first ranking for the base configurations. Okay, so this matrix considers the techno-economic regulatory dimension of STOR-HY, and it encloses the ranking in terms of capability of providing ancillary services to the grid from each of these plants. So in the preliminary version, only the base configuration or existing configuration will be evaluated. And the ranking will be based on a traffic light system, so it will be qualitative and will just give some preliminary evaluation of the capability of this ancillary services provision. This is the color system that we're using to fill in the matrix. So in red, when the plant is considered not to be capable to provide that service. In yellow, when it is considered capable, but with a limited capability that in some cases can be enhanced with the technological solution proposed in STOR-HY. In green, when it is currently capable of providing the services, in some cases also already participating in the services market. In gray, when the plant is still in construction, as we say, this is the case of Pozo Figueiredo. And in black, where this ancillary service is considered not to be applicable to that particular configuration of the plant. And we will see further on what this means. So this is the structure of the matrix. I will go through the different components of it. So in the top part, there are the ancillary services, and in the bottom part, the traditional definition for those. So synchronous and synthetic inertia and in the field of inertia. Then there are the frequency support services in order of rapidity of operation. Then the voltage and VAR control, and finally the black start operation. On the left side, there are the demonstrators that I just presented to you. And on the right side, there are the different technological solutions that will be developed for each demonstrator, particularly the ones that have some impact on flexibility. So here there is the legend that explains. So in the base configurations that they are all considered to be fixed speed. In some cases, variable speed will be implemented. In some cases, just a reduced scale power converter, and hydraulic short circuit and hybridization with batteries and photovoltaic. On the bottom, there are the emerging European framework that Fernando explained to you for the different services. And here is the legend of the colors, just to start filling up this matrix. So first of all, as we said, the black dot means that the plant is not considered to be applicable for that particular service. And this is the case for synthetic inertia and fast frequency response in fixed speed units. Because of the hydraulic, for the dynamics of the hydro units, it is considered that these very fast services cannot be provided. So it does not even make sense to evaluate this ancillary service. Then another line that is kind of excluded by this first ranking because of the fact that the plant is still in construction, but we will fill it up in the course of STOR-HY, is the line of Pozo Figueiredo, which we decided to not assess for the moment, as it should be just an estimation. So yeah, the plant is still in construction. Then passing through synchronous inertia, this capability is evaluated with the inertia constant of the hydro units. So it is considered to be provided by all of them. The one that performs slightly worse is Laurence, which has a lowest inertia constant. Then moving on to the frequency support ancillary services. In pump mode, since this is fixed speed, the pumps are considered not to be flexible and just to operate between either at 0 or at rated power. For this reason, they are considered not to be able to provide these services on command. So they are excluded from this evaluation. On the other hand, the turbine mode are already capable in some cases of providing these ancillary services. As we can see, in some cases they are green, in some cases yellow, in some cases even red. And these are information that we gained from the demonstrators. So in some cases, these plants are already participating in ancillary services market. And in particular, for the case of Alkeva, we already have information from the previous project, Xflex Hydro, that shared with STOR-HY this demonstrator and assessed the capabilities of ancillary services. Moving to voltage control, we obtained this ranking from the nominal power factor of the plant, which relates to the capability of providing reactive power. And we see that in most cases it is quite good, except for Larance that has a relatively low, high capacity power factor, sorry. Finally, in Black Start, we see that none of the plant is capable currently of providing the Black Start service except for Le Sheila, which is characterized by a startup time of 5 minutes and a ramping capability from 0 to full load in 2 minutes. So this is the current version of the matrix, the preliminary version that will be then filled up along this project. So our next steps will be to transform this ranking from a qualitative traffic light type ranking to a quantitative system. So obtaining some numbers for which we will need to perform some simulations that will be enabled by the development of models for the different demonstrators that will be developed along this project. And also to evaluate the improvements that the technological solutions in the different demonstrators will bring, particularly in terms of flexibility. So our expectations for these improvements are that variable speed will enable the provision of the very fast services that Fernando explained to you, so synthetic inertia and fast frequency response, and will also generally increase the flexibility of the plant, even in pump mode that is currently considered not flexible. The implementation of hydraulic short circuit, that means operating the pump and the turbine at the same time, enables to regulate the net power when in pumping mode. So if the power of the pump is fixed, by regulating the power of the turbine, the net power will be the net power absorbed by the plant will be regulated this way. Then the hybridization with batteries and photovoltaic will also enable faster responses, so faster frequency support services, and also improve the services that are currently being provided. And there are also other flexibility-related features that are not directly categorized as ancillary services that can be improved by these solutions, for example, the market participation or the capability of shifting the load. As we said, this first flexibility matrix only considers the techno-economic regulatory part, so the flexibility side of these demonstrators and the improvements. So for the next sections about the environmental aspect and the social aspect, I will leave the word to my colleagues.
Hello, everyone. Now let's move on to the environmental and economic dimensions. I'm taking over the slides. All right, so in this session, I will present 3 key components. I will start with the process of indicator selections and then what indicators we have selected. And then I will briefly explain the methodological approaches that we will use to quantify these indicators. So we started with selecting which indicators we will measure in this deliverable, and the assessment will be done in the another work package 7, and then results will be integrated back to the STOR-HY metrics. So for this, we will use the combination approach of practice and science. On the practice side, we are developing the assessment models and collecting the necessary data for the case studies for each demonstrator site. On the science side, we have explored different indicators and existing methods for the development of the new indicators and improve the methods to quantify the environmental and economic dimension. So this is basically the general approach and overview of our plan. So here I would like to explain a little bit more about the process of selecting the indicators. There are many possible indicators that we can use to quantify the different aspects of environmental and economic dimensions. First, we try to keep it open to explore what indicators are available. We did literature search to collect all the possible indicators from international standards, guidelines, and scientific papers. Initially, it was like a big menu card with a lot of possible indicators and options. We presented the initial selections of these possible indicators to our project partners so that they could provide us their inputs and suggestions. Then we came up with the final selections of the indicators, which was also proposed and presented to our project partners for the final selection. Now we have this final list of the indicators, and we will continue the quantifications of this indicator in another work package. So what are the indicators that we selected? Basically, there are three environmental indicators, three categories of environmental indicators, and one category for life cycle economic indicators. For example, for environmental indicators, we have biodiversity impacts, in which we will measure the local biodiversity impacts, which is occurred due to the on-site hydropower operations, and also supply chain impacts, supply chain biodiversity impacts. I will in more details in the later slides. There are also other impacts such as life cycle impacts, which will cover the carbon footprint, water footprint, land use changes, and resource dissipation. There are also circularity indicators, which cover the resource dissipation and recycling rate. And for the economic dimensions, we will use the CapEx and OpEx. So by combining these indicators, we will integrate the results into the story matrix. So this is how the story matrix will look like. This is the preliminary example of the story matrix for the economic and environmental dimensions. As you can see here, the first column in the table is the list of our demonstrator sites. The other column represents each environmental and economic indicators that we will quantify. The row here at the bottom is the assessment approach that we will use to quantify each environmental indicators. We do not include the traffic light system here yet because the quantifications of this indicator will be conducted in another work package 7. So moving on, I will briefly explain each of these environmental and economic dimensions and how we will measure these indicators. So the focus of this part is more on the scientific approach that is a part of our PhD research. So biodiversity is one of the key indicators. It is a complex and broad area, so the scope of the biodiversity impact could vary among different stakeholders. In some assessment approach, as you can see here, biodiversity impacts are mainly described from the perspective of the local impacts due to the on-site constructions and hydropower operations. This include impacts on biodiversity due to land use changes, water temperature changes, flow alterations, sedimentation, and collision of the living organism with the hydropower infrastructure. And there is also another perspective on the biodiversity impact, which is described from the supply chain perspective. For example, the construction material used in the hydropower are manufactured in somewhere outside this project area. For example, like steel and concrete are manufactured outside this area. So the productions of this material can causes the greenhouse gas emissions or the release of toxic chemicals, which is occurred throughout the supply chain of these materials. So these impacts can be described as execute or supply chain impacts. So these are the two different perspectives on the biodiversity impacts. And in our analysis, we will cover both local and supply chain biodiversity impacts. So how do we measure these biodiversity impacts? First, we will start with the life cycle assessment model in which we will quantify the supply chain related biodiversity impacts due to the environmental pressures, as you can see here, like climate change, ecotoxicity, and water use. From this LCA model, we will have the biodiversity impacts in terms of potentially disappear fractions of species, which is one of the key aspects of the biodiversity loss. And then we will use the local biodiversity assessment model called Globio Aquatic, in which we will quantify the biodiversity loss due to the site-specific pressures here. This model will provide the biodiversity loss in terms of loss of main species abundance, which is also another indicator of the biodiversity loss in the local area. So, and then we will try to combine these two biodiversity indicator into one single indicator so that we can compare the biodiversity assessment results across different demonstrator sites and other alternative technologies. And the second categories of impacts that we consider is the life cycle impacts. So this diagram here is the general illustrations of the life cycle of the pumped storage hydropower plant. Throughout its life cycle, it uses the inputs such as water, resources, and land. And also it releases the outputs such as emissions and waste. So this consumptions of resources and releases of emissions might cause other impacts such as climate change, water use, land use, and resource depletions. So in our analysis, we will cover these impact categories in addition to the biodiversity impacts. And when we quantify these impacts, some parameters could vary temporally, which can affect the results of these impacts. For example, if the electricity used for pumping water to the upper reservoir comes from the grid and the grid mix vary temporarily, the environmental performance of the pump storage system could also vary. So this issue was not reflected in the previous scientific research, and we will consider these temporal variations in our analysis. So to quantify these life cycle impacts, we will use the life cycle impact assessment approach. First, we will start with the conventional way of doing the LCA. In this conventional approach, we don't consider the temporal variations first. Therefore, we can quantify these impacts in terms of the static results. And then we will improve this assessment approach by integrating the temporal resolutions in our analysis, such as the variations in electricity mixes, reservoir emissions, and storage technical improvement solutions. So this assessment approach is called the dynamic approach, which will provide us the LCA results in terms of the dynamic results. By comparing these two sets of static and dynamic LCA results, we will be able to see how considering the temporal variations can provide more realistic results. And the next indicator that we consider is the material circularity. When hydropower projects are decommissioning, one of the possibility is to deconstruct some infrastructure, which will generate construction and demolition waste. Some of these waste can be recycled, which will provide a supply of the recycled materials to some other industry in the future. This will hypothetically decrease the demand of the primary materials, also the production of these primary materials. So when you decrease the production of these materials, it will also decrease the environmental pollution from this production process. So the circularity of these construction and demolition wastes are important to understand a more complete picture of the environmental impacts and even possible environmental credits in the pumped storage projects. So this is why we will consider this indicator in our analysis. Our methodological approach for this indicator has two steps. First, we will focus on the current conditions. We will estimate the quantity of the construction waste, such as concrete, steel, and copper, from the decommissioning phase. Then we will set the circular economy scenarios considering the current practices and conditions. Then we will conduct two assessments. The first one is how circular material is in the circularity assessment and how much the environmental impacts might occur under each scenarios. So this part of the assessment will give us the circularity and environmental consequences under the current conditions. But then these conditions could change in the future because the PEM storage project has a very long lifespan. So we need to forecast the future conditions for this circular economy scenario. To do that, we will review other supplementary models and incorporate the outputs from this model to our analysis, which will improve the scenarios that we develop for the future conditions. Then we will repeat the process of circularity assessment and life cycle assessment to get the results in terms of the future scenarios. So in the final step, we will have to set off results for the current conditions and future scenario, which can be used for better understanding of the potential environmental trade-offs and credits for policy making of the decommissioning phase. And the next indicator is the environmental dimensions. So to analyze the economic impacts and viability of the PEM storage, we will develop and implement a comprehensive lifecycle cost analysis model. In this lifecycle model, we will consider two key economic indicators, capital expenditure, CapEx, and operational expenditure, OpEx. And we will also introduce three components listed here on the left side. So the first component here is I think I have, can we return to the previous slides? All right, sorry about the inconvenience. So the first component that we consider is the considerations of the decommissioning cost and how it affects on the life cycle costing, because the currently available decommissioning tools do not cover all the relevant decommissioning costs. So we will identify all the relevant cost elements and variables to develop a decommissioning tools for the STOR-HY project demonstrator sites. The second component we will consider is the market and energy price volatility. Currently, the financial performance of the PEM storage facility mostly depends on the price difference between the energy purchased during the off-peak hours and energy sold during the peak hours. So in our model, we will consider the market and energy price volatility to de-risk the PEM storage investment and operation activities. The third component that we will consider is the climate change impacts on the hydropower operations. We will try to understand how changes in the precipitation and temperature patterns will affect on the PEM storage activities and to evaluate their impacts on the life cycle cost of the PEM storage system. So this will help us to determine whether these changes will have a negative or positive effect, particularly on the PEM storage operations. So this is the overall timeline of our part, and we are right here at the month end, and we'll continue working on the quantification in the following month in the work package 7. So a few key takeaways. I talk about the environmental dimensions and economic dimensions. Under environmental dimensions, we have a total of 6 indicators, 2 biodiversity 8 indicators, 2 biodiversity indicators, which will be potentially combined into a single indicator, 4 life cycle indicators, and 2 circularity indicators. And for economic dimensions, we have 2 indicators, CapEx and OpEx, and these indicators will be quantified in the work package 7 and incorporated back to the STOR-HY matrix. So this is all from me, and I will hand over the presentation to my colleague Jason from NOS. Thank you.
Perfect. Thank you very much. And I think you gave people a little bit of an appetite of what's coming up in my slides as well. So maybe they'll have caught a glimpse very quickly, but I'll just take control now, and then I can go through the slides and give a little bit of an overview. Just while I'm waiting for that to go through, I can probably give a little bit of a taste as to what we're actually going to discuss here. So as you've seen, perhaps in the agenda, this is going to take around 30 minutes. I probably will go a little bit quicker. Generally because I speak quite quickly, but that may be part of the reason, but we'll see how it goes. So what I'm going to try to discuss and take you through here is essentially a couple of different stages of where we are in terms of the social dimensions within the STOR-HY project. What I want to start with is probably relatively elementary for many people on the call, but I think it's important to give the context as to what we're actually trying to do and how we've considered the social dimensions or social indicators that we ultimately select and will take forward into the next stage, which is essentially the data collection. So we will be looking at a little bit about how we consider social acceptance, sort of what we know from theory, what we know from the meetings that we also had with the demonstrators in terms of how they understand social acceptance, what types of indicators they use. I think that's an important contextual bit of information. I think then what we also want to do is how that sort of influences indicator selection. So obviously we're trying to distill it down to sort of core themes or core categories. That's an important aspect that we have tried to be relatively patient with over the last couple of months and try to not presuppose too much what indicators we want to include, but which ones are used and which ones are recommended to be used. Then we sort of look at the indicators that we selected, then switch into how we'll actually operationalize those indicators. So what are we actually going to do to capture those values, and how is that going to be considered and ultimately represented within the STOR-HY matrix? So if I can see if it works, which it should do, if I click somewhere, there we go. I think if we're going very much back just to social acceptance more generally, I think again it is a little bit relevant here because it's an important bit of contextual information that we need to understand. Generally, what kind of questions we use to motivate ourselves, which is generally the title of these slides as I go through the first couple, are sort of why does social acceptance matter in energy projects? Generally, we can kind of consider this as sort of technical challenges, but as we're all too well aware, this is often not why projects stall or get delayed or get pushed out. Generally, major infrastructure projects face public resistance, delays, challenges in court. We've seen big cases in Norway with some onshore wind that have been delayed. I'm sure there's many examples, and hydropower is certainly not immune to that. So it can come down to these issues of community buy-in, engagement, trust. These types of factors can be quite important, rather than purely technical limitations, which my colleagues previously mentioned quite comprehensively. So here, what we're sort of using when we're thinking of social acceptance is not purely thinking of it just a technical process. It's also negotiations of our land, livelihoods, local futures, conceptualizations of fairness, trust, equity. These types of values are quite important, and I'll come into why, particularly in hydropower, but in energy projects more generally. Across Europe, we can see that this is a relatively big component in whether they're ultimately successful and developed, or whether they're stalled and ultimately falter and maybe fail. So while public opposition is often framed as NIMBYism, this not in my backyard, it can also kind of reflect these deeper concerns. So it may be, from our perspective, a little bit reductive to think of it as purely NIMBYism. That's not to say that it's not sometimes a consideration or oftentimes a factor, but what we're obviously interested in is getting to the deeper issues. We're not just interested in sort of being a sort of channel for NIMBYist concerns. It's much more about, are there actually legitimate, genuine concerns that people have about sort of trust with the developers or trust with project owners, whatever else it may be, and is there issues of fairness here? I'll come back to that in a moment. So what we're kind of interested from the social acceptance angle, and what we've kind of spent a lot of the last couple of months trying to figure out, is sort of how can we understand this broader viability of projects when we're looking at something which is often seen as a sort of impediment or barrier to these projects, you know, being developed or being updated or adapted or improved in whatever regard. So this is sort of a big part of why we're interested. I think if I come to the next slide, there's this lovely GIF, which I think is probably a little bit too elementary for most people on this call, but I think it's quite useful when I've tried to use this to discuss this project with others. So getting into the kind of social acceptance challenges of pumped storage, hydropower in particular. So as was mentioned in the preceding presentation, these types of projects can often involve large-scale landscape transformations. There can be new reservoirs, tunnels, grid infrastructure, and these can have both visible and long-lasting effects on local environments. And communities can obviously have concerns or perspectives on whether that's a good or a bad thing. But there's also this sort of issue where a lot of these projects are typically situated in maybe more sparsely populated areas, maybe protected areas, where ecological values and rural livelihoods are also closely intertwined. But I think also what for us is quite an important component from what we've discussed is that local communities may very much be asked to bear the brunt of the environmental burden and the social burden of such projects, while the benefits, grid flexibility, national resilience may be distributed elsewhere. And this can sort of impact upon the sort of resistance which we see. So if we look at the other side of acceptance, we can look at resistance. And I suppose this is sort of where we can kind of see that these types of things can come, because it can be seen as completely unfair that we have to face the burden of looking at this thing or dealing with the road network disruption or the dust when they're redeveloping these sites, and the benefits are being felt far, far away from us. So how do we make that a bit of a fairer trade-off? And also this sort of long lead time of these types of developments can mean that developers must maintain trust over extended planning and permitting periods. Not to diminish other energy sources, which I mentioned on the previous slide, but on others, they can be developed and implemented much quicker. These can take quite a long time. And that also puts different pressures, because we will discuss how we consider social acceptance, but it is, as in our understanding at least, a dynamic process. And that means over the life cycle of these projects, for example, or the development of these new sites, or the changes to these sites, social acceptance can ebb and flow. People can change their perspective. What they initially thought was good and fair and right are now seeing is too burdensome, and that can sort of lead to an evolution in how people perceive these types of sites and these types of changes. And there's also this particular aspect which is probably quite relevant here in the STOR-HY project, which is that site updates may reactivate earlier conflicts and concerns, increasing the risks of previously kind of resolved challenges resurfacing. So essentially what we mean by this is projects which may have been initially developed in the 60s or the 70s or the 80s, now going through periods of updates, may reignite earlier conflicts, may reignite contentious debates about the very presence or the existence of these sites, which were largely put to bed while the site was in a kind of operational phase. Where you're now talking about changes, that obviously brings up new issues and may lead to the reemergence of older issues as well. So if you're like me, you're probably getting a bit dizzy from this GIF on the side there, so I'll switch on to the next one. So what do we know about the social acceptance in the energy sector? So a lot of this work kind of goes back, and we give a little bit here of the theory and sort of what we've sort of looked at in terms of the indicators that are recommended to include, what sort of the evidence base tells us about the different types of factors which are important in social acceptance more generally. So there is, perhaps you've seen it, perhaps not, you may have seen this triangle of social acceptance, which looks at the different types of acceptance which are required. And of course here, there's obviously aspects here where different stakeholders are represented across these, right? So socio-political acceptance obviously includes the public, but the public may also be consumers, which deviates into market acceptance. And then that also is the broader community issues around trust. So, you know, there can be these challenges that kind of cross-cut, but I think there's been a lot of work in recent years on sort of updating on from this earlier framework, I suppose. So a lot of the work now is linked to perhaps what's more clearly capturing community acceptance, this sort of deeper issues of procedural fairness, distributive justice, and recognition. So I think there is much more of a need for what we consider at least a bit more of a dialogue is perhaps more, rather than capturing it as, you know, a thermometer in the water and taking the temperature. It's a bit more about building that social acceptance through dialogue, through understanding concerns, and through sort of addressing them in a sort of mutually beneficial way, if at all possible. And that's sort of the trade-off that we're obviously trying to capture here. There is also issues around trust. This is obviously quite important. Trust in developers and public authorities is seen as a quite key predictor of social acceptance. A lot of the literature that we look at, I mean, most of the literature I try to refer to here is based in Europe, but a lot of these are mainly about newer developments. And obviously then there's different considerations. I think with some of the demonstrators that we spoke with, they were obviously quite interested in talking to us a little bit about their ongoing or their developing sites, I should say, in perhaps newer markets or emerging markets. But I think the considerations there are potentially different than the context of the STOR-HY project. So for us, we obviously try to make sure that we're not just following this blindly. And I think that's why we think trust is certainly something we've considered and the types of indicators that we've developed. And it's also this kind of early transparent engagement often can shift opposition towards a sort of constructive participation. So it's partly about this idea of sort of listening rather than just sort of bulldozing over concerns. That can also be quite an important way to build that social acceptance and build that sort of understanding as well. There are, of course, gaps within the literature, within a lot of the academic literature that we reviewed, the empirical literature, about plant upgrades, refurbishments, and changes and how they impact upon social acceptance. So that's obviously for us an area that we're quite interested in and one we'll obviously be exploring quite closely in the STOR-HY project. But it does mean that we're operating here somewhat without that clarity of what that actually means in that context. So there is limited literature which we've reviewed, but it obviously doesn't go into as much depth as building a new hydropower plant in a new area. That's obviously completely different considerations than refurbishing an existing one. So moving on from that. So now that we kind of have that and we have that kind of contextual background, what I wanted to do is switch a little bit towards capturing our approach to social acceptance, or how we capture social acceptance. So as I mentioned, we do recognize social acceptance as a sort of dynamic process. And I think this is not just simply a buzzword for us, it's also how we've considered our methodology and how we considered that process of actually capturing social acceptance, not just as we conducted a survey at the start, people were excited, we conducted it at the end, people were not excited, and something happened in between. That's not what we're interested in. What we're interested in is how that process sort of ebbs and flows and evolves through that sort of life cycle of changes that take place. And of course, we do have some standard, perhaps more qualitative approaches. I'll come to that in a second, but we also have this newer sort of emergent approaches which are being used to sort of better capture this sort of dynamic nature of such changes. So this is sort of shaped by how people experience the environmental, economic, and political impacts over time and in space. That is quite an important aspect for us. We rely on, as I mentioned, both qualitative interviews with stakeholders, and I'll come to that in a second, a little bit about, what types of factors are we considering in those interviews, but also how do we identify those stakeholders, which I think is quite important to make sure that we're being inclusive, or as inclusive as we can. But also this media discourse analysis approach. So as I mentioned, my background somewhat comes from economic geography, and I noticed there's a lot of interest in this type of method, this type of approach within that field. But also I think more generally it has a lot of use cases. And this is sort of looking at both traditional and digital media as how we've considered it. So basically being able to capture online discussions that go on, but also being able to capture opinion pieces, press releases, those types of things that also appear in more traditional media around the sites, to understand the evolving discussion that takes place about these sites and the changes and those types of considerations. So what we're kind of interested with that is capturing both the individual perceptions and sort of being able to generalize somewhat from that. What do we know about how these stakeholders feel about it? But also, and I'll come back to this again, is about this sort of collective narratives. So what we're interested in capturing is narrative forming, narrative shaping, and kind of how narratives evolve over time. What we mean by that is essentially how our initial stakeholders in the area, I know here, for example, where I live now in Norway, there's quite active discussions in local media about pretty much every issue. And it's sort of capturing those discussions that go on between members of community, members of the society, and members of sort of industry and those types of things, and academic stakeholders as well. In this kind of public realm is obviously what we're trying to capture there. So as I mentioned already, rather than treating social concerns purely as barriers, we view them as kind of important feedback. And this is sort of what we want to represent within the story matrix, the variables that we've captured, because we want to be able to sort of isolate, or at least understand, how the individual categories affect collective social acceptance scores. So rather than, I'll come back to that again. I know I seem to be saying that a lot, but it's all linked in some way. So that sort of makes sense. We see them as this sort of approach for better feedback and governance and communication at the plant update. So it's about sort of learning and developing rather than just simply saying, yes, we're good to go. Society loves it or hates it. And then proceeding ahead anyway. It's much more about that sort of dialogue I mentioned. By connecting these technical planning with social insights, we aim to contribute to a more sustainable and socially responsive pumped storage hydro projects across Europe, which is our general motivation. So I'll go through this very quickly because I also have it on the next slide as well. But these are the sort of 6 dimensions of social acceptance that we're looking at in STOR-HY. So essentially, this was the culmination of the process, much the same as So mentioned in the process they used. We also had a similar process. And this is sort of the categories or the conceptualization we looked at. So first was environmental responsibility. Again, this is to stakeholders, not similar to what So is doing, for example, in his work package. This is looking at perceptions of ecosystem disruption, mitigation effects, long-term impacts, sort of how people feel about those disruptions or those effects rather than those effects themselves, right? So whereas I come back to it, I think in number 4, this sort of trade-off dimension as well. How do people consider those trade-offs? Also looking at community involvement and trust. So here we're looking at stakeholder engagement, transparency, trust in the institutions, trust in the demonstrators, trust in general. So essentially this is about capturing how people consider themselves to be heard, how they consider themselves to be involved in that process in some way. Then looking at sort of the economic and employment effects, much the same as in the first dimension. This is looking at economic benefits, job creation, and regional attractiveness. So again, looking at this from a perspective of public perceptions or stakeholder perspectives on these types of benefits and trade-offs and what that does to their general acceptance. Then, as I mentioned, this, public perceptions a bit more generally. So getting a little bit more explicit about those trade-offs. So the benefits, understanding of renewable trade-offs in more of an aggregate sense. Then health and well-being, so concerns about health effects from plant upgrades. And in this, we obviously try to tease out a little bit about what they may be, whether it's increased dust from changes on large changes of trucks coming in and changing out equipment or whatever it may be. So it's about kind of framing that conversation that's local and specific to the individual site, but also is informative to us about whether this is a concern which is shared or held. And then also looking at this sort of ongoing legitimacy support and community alignment. So this is much more about that temporal perspective stretched out a little bit. So sort of an understanding a little bit, I would say, more clearly about how that time effect influences social acceptance. So I think here is our preliminary version of the STOR-HY matrix, story matrix. And again, this is relatively straightforward. So here we have the categories from before, the dimensions from before. And of course, as you can see underneath, you can see weightings. That's the weightings that we've done relatively. At this point, it obviously requires some contextualization on the sites, and that's obviously to be done in engagement. This produces a sort of social acceptance score, and this will also be represented in the matrix. So this is sort of a composite measure, I should say, of all of these. And then a lot of these are constructed from these stakeholder interviews. So a little bit then switching into a little bit about the method, conceptual overview of our method. So obviously, as I mentioned, we have these two different approaches to qualitative analysis, which first looks at this identification of relevant stakeholders. So we've already began on that process of outlining the sort of schematic to be used on each site in terms of how do we identify the stakeholders that are relevant in this context, and how can we get informed information from stakeholders themselves, but also from the demonstrator sites about which are the most relevant for us to be speaking with. Then obviously the data collection approach is through structured interviews. And then it's an analysis of that qualitative data. So this is again looking for emergent themes. This is likely going to use thematic analysis. I think we have that outlined in the document that we've prepared already, but it's I think it's probably a little bit, well, not maybe so necessary here. And then in the quantitative analysis, this is again looking at the media discourse. So this is again looking at the types of media that we're interested in, the identification of the relevant stakeholders, both digital and traditional, and then also conducting that media discourse analysis. And I think in this, there's still a little bit from our side about, I suppose, teasing it out once we start on the actual data collection process, how that integrative analysis is conducted. So how is the weighting of the media discourse analysis reflected in the kind of general social acceptance score? So that's something that we're kind of considering for the next stage. Next, then we move on to this identifying and engaging stakeholders. So as you can see here on the left is an example from the document we've been working on, which is sort of examples of the types of stakeholders that we're actually interested in speaking with. So here, the stakeholder mapping process identifies and categorizes actors involved in or affected by pumped storage hydro projects. And this is, again, on the left side, relatively comprehensive, again, based on that analysis that we conducted of the existent literature and having spoke to the demonstrators themselves, to give us a bit of a clearer overview as to who actually we should be trying to target and who should we be trying to involve in those structured interviews. So the mapping is very much focused on sort of ensuring this sort of balanced participation from supporters, critics, and those with a neutral perspective on pumped storage hydro. So as we understand that, our objective is to sort of capture the diversity of opinions that people have about the changes that are taking place. And that's obviously a big part of what we're trying to do. So we obviously want to expand that net as broad as we can to make sure that we're being as representative and sort of inclusive as we can be. Engagement strategies are obviously tailored to the needs and roles of different groups. So obviously some are going to be much easier to reach out to than others, and obviously it requires some sort of contextualization when we're actually conducting the data collection. That's going to be in line with, the scale and the scope of those different sites. That obviously needs to be made. That needs to be adapted here. The mapping process is generally dynamic and contextualized to each site. So again, at this point, it's very much about being open and being relatively responsive to changes across the different sites that we're looking at. And it'll be regularly updated as new stakeholders emerge or contexts evolve. And that's the kind of approach that we're trying to stick to. And essentially, the mapping process is kind of aiming to ensure a sort of broad representation and upholds our sort of commitment to inclusivity and fairness, which we think is kind of important if we're going to capture this in a quite comprehensive way and if it's going to be useful in the future. So a little bit more about the methods and why we chose the methods that we did. So the structured interviews were chosen because we think this allows us to explore how key actors understand the changes across the different dimensions. It's seen that it's much more, the document which we prepared has headline questions, which we've tried to enable that there's a possibility to be able to quantify them. So there's a sort of initial Likert style question, sort of a 1 to 5, agree, disagree type thing. And underneath that, there's obviously a lot of sub questions to sort of tease out a little bit about why such an answer, because that's what we want to understand. Is not just, the what of what do they feel, but very much about the why. Why do they feel that way? What is the factors that would potentially lead to change? So that's where the thematic analysis aspect comes in. The interviews provide sort of an in-depth insight into how individuals perceive and make sense of the hydropower projects, revealing the different understandings of acceptance and concern across the different social groups that we're interested in speaking to. And the media discourse analysis, which my colleague Mia is sort of leading, tracks a little bit more about this, how projects are discussed in local and national outlets, revealing narrative formation, frames, and interactions among stakeholders, which again, I think I've mentioned already somewhat, but I think it's also an important part that we're trying to capture here, and it's important that we explain that aspect. So once we combine these two, the qualitative and quantitative, we get this sort of mixed method or multi-method, I should probably say mixed method approach, which helps, we hope, to avoid blind spots and answer both the how and the why questions. And the data is to be collected, obviously, as I mentioned, the next work package, iteratively and contextually, and that will start, I think, from the end of this year, beginning of next year, allowing our model to reflect changes over time. So with the interviews, those are obviously going to be, snapshots, moment in time, or that period at least, where the interviews are conducted. But the media discourse analysis allows us to go back quite a bit in time, and also allows us to go right up until today, until pretty much real time, or as close to real time as possible. I think then I have a little bit here just about how we actually have considered quantifying social acceptance. So as I mentioned, this is obviously the problem with the qualitative data, is it'll be harder to fit into that matrix. So we've obviously considered that or built that with that in mind. So here, for example, you can see the dimensions that we're looking at. You can look at the dimension weighting to the composite measure, which is the social acceptance score. We have the questions here, which is linked to our interview guide. And then we have the weighting per question. And that weighting was sort of defined with some sort of discussions with the demonstrators in mind. But it also, as I mentioned, in some, there's going to be contextual information that means it needs to be modified. So the interview guide is, obviously a template to build off of. But I think for us, this is sort of the aggregate of how we would consider it in an optimal situation. But it obviously will require some adaptation or some local adaptations, I suppose. So again, we're using this kind of structured scoring system, which I mentioned in the questions. And each dimension is then assessed using site-specific indicators and assigned a weight based on its perceived importance and salience in the local context. So that's a little bit more of a dialogue to come to that question, or to come to those weights, the final weights. And then sort of our model uses this somewhat simple formula. We've tested it recently enough. We tested it just before we broke for summer here in Norway, which was back in June. And we sort of used this sort of aggregate data just to basically see how it would perform. And it was, the interpretations of the data were actually quite helpful because it enabled us to sort of isolate the effects of what sort of dimensions are driving or impeding social acceptance, which may mean that there's a potential to get a little bit more contextual information and perhaps understand things at a deeper level rather than just saying, from our perspective, that social acceptance is very positive or very negative. It's also about where is it positive, where is it negative, and why is that the case. So I think then I can kind of wrap up. So this is where I tie all those strands that I mentioned back together. I think I've probably covered everything relatively comprehensively, I hope, but I also hope there's some good questions to discuss. But I think what we've sort of built so far, or at least where we are now at the culmination of the task, work package 2, is sort of this multi-dimensional framework to assess social acceptance across those 6 key dimensions. It's also this sort of mixed method combining interviews and media discourse analysis, both of which have been tested with relatively small sample data, but it's obviously a way for us to validate it. A weighted scoring model that quantifies social acceptance across those categories, an integrative assessment, integrated qualitative insights for clear and broad-based assessment, and then sort of a roadmap to ensure inclusive, ethical, and site-specific stakeholder mapping. Where we are now, or at least what we have remaining to do, or will now switch to doing, I suppose, would be this sort of refinement of the media discourse tools, including framing and sentiment analysis for capturing diverse narratives. So we will be presenting, I think, a version of this at a conference later this year as well, because I think this is kind of an interesting, interdisciplinary or cross-disciplinary approach that we can use in this context. So it's obviously refining that and making sure that is built as it should be. But then it's also switching to data collection through the interviews and media discourse analysis to assess the social acceptance. So then it's sort of switching into operationalizing what we have outlined here as our approach. So I did say I would be a little bit quicker. I didn't think I'd be 4 minutes. I thought I'd probably be 4 minutes over, not 4 minutes under. But that is where we are on the social acceptance side.
Thank you very much to all of you for all your valuable contributions. I think this gave a very complete picture into what has been going on in work package 2 of STOR-HY. So now we can move on to the Q&A. I don't know if anyone in the public has any questions. If so, you can, if you are able to raise your hand and I will give you access to your microphone, or directly write them in the Q&A section. Maybe we can wait a few more moments in case someone is typing. If not, I do have a couple of questions that maybe we can tackle in the meanwhile. So for Fernando, I was thinking, how does the flexibility provision of pump storage plants compare to other renewable energy sources, such as wind, solar, and also with conventional hydropower plants?
Yeah, well, wind and solar energy, so there are really high expectations for installing these power plants in the up to 2050. They will be the dominant sources of clean energy, let's say. And the fact is that in terms of flexibility, they are considered variable renewable energy. So in terms of flexibility provision, there is really not a good flexibility to be exploited from them if compared to pump storage plant. Because if you can think of wind and solar generation, you can only generate when there is wind or when there is sun. So, and if you want to be able to exploit something like frequency containment reserve in a moment when there is sun or wind, if you want to be able to provide this service, you need to deload or to exploit these sources with losing in the energy market so that you can exploit the flexibility. So I would say that pumped storage plants are really superior to wind and solar technologies regarding flexibility. And if we compare with a conventional hydropower that has no pumping capability, the fact is that pumped storage plants have much more flexibility capability, because they will be simply recycling the water, so they are also superior to this kind, to the traditional hydropower. So what's important to say is that pump storage plants have a really good future in terms of complementing these other renewable energy sources in the future. That's how I would put it.
Perfect. Thank you very much. And we've received a question from Antonio Aires. Thank you for that. What are the expected next steps in each of these dimensions? And here he also thanks you for the insightful session. So maybe we can do a bit of a short roundtable, and then you can each mention whatever comes to mind. Do you want to start, Sophia?
Okay, I already introduced some of the possible next steps, at least in terms of flexibility, which is our domain of study within STOR-HY. Maybe it can be useful to go back to the slides on the demonstrators, because I think from the characteristics and the improvements that I presented, there are also some things that are clearly directed more towards the environmental side. So, okay.
Just let me know when I'm there.
Okay.
I'm sorry for
the first
taking-
one, no problem, sorry. Okay, this is,
Okay.
I don't know, Vuglam is the first one. Okay, can I maybe take control again? Okay, so from Vuglan, the improvement in terms of flexibility will be mostly related to the addition of pumping capability in the downstream plant, so the one between Somortier and Coiselet. So this is an enhancement in terms of storage capacity. And also among the features that we have in the matrix, if I am not wrong, there is yes, okay, it is also here. The second pump that will be installed will also be provided with variable speed, so connected with a power converter. And variable speed allows for a pump to regulate the power more flexibly, so also to provide different ancillary services from the pump, which is installed between Somortier and Coiselet. So I would say from Vauglin, this is the biggest improvement in terms of flexibility. For Sheila, this innovative mode change provided with fast dewatering will increase the flexibility, the fastness of response to some signals that can be market signals, but in general it will make the plant more flexible and more rapidly able to change between modes. For Larance, the flexibility enhancement will be mostly connected to the addition of battery. So as battery is able to respond very fast to control, it can provide ancillary services, it can provide faster response also to market signals, so also reach higher revenues from the electricity market. From Alkeva, similarly, we have the addition of this battery that can also in the next step, when we will delve into the siding studies, also be enhanced. So, and also when, of course, the solar resource, as Fernando mentioned, is available, also the photovoltaic can be involved in the provision of ancillary services. Then in Villarino, the flexibility will be achieved mostly with the mechanical operation of the inlet valve. And also with a hydraulic short circuit, since we have a turbine and pump operated separately, so they can also be operated at the same time and perform this hydraulic short circuit, so that the net power input in pumping mode can be regulated through the regulation of the turbine power. And in Pozzo Figaredo, I would say that most of the flexibility enhancement will come also from the hybridization. So still with the battery and the photovoltaic system that can be installed in the site. And this is what we expect mostly in terms of flexibility enhancement. But I can also move to the metrics to consider what are the different technological solutions. So we have some of these plants that involve hydraulic short circuit, some that involve the hybridization, and in case of Vouglans, we also have variable speed. So yes, I would say this is mostly what we expect in terms of flexibility. I don't know if maybe So can say something about environmental benefits that can come from of these demonstrators.
Yes, thank you, Sophia. On our side, for the environmental and economic dimensions, there are two key components. The one that I mentioned in the presentation, the practical side and the science side. On the practical side, we are currently in collaboration with our project partners to collect the data for the case study that we will develop for each demonstrator sites. And on the science side, we have been exploring and developing the methodological approach that we use to quantify the indicators that we have selected in this work package. So basically, the next step is to implement the models that we develop on the science side with the data that we collected for each case study of the demonstrator site. So this is what we plan so far for the next step. Thank you. Maybe my colleague Jason will mention something about the social dimension.
Yeah, thank you very much. Yeah, exactly. So I think for us, it's relatively switching into the same approach now. So I think it's very much getting into discussing a lot more about collecting the data, and that's obviously going to be done in conjunction with the demonstrators themselves. So as I said, we have the kind of outline, the large yeah, we have everything basically covered in those dimensions, or we have the things that we're interested in approaching covered in those dimensions. And now it switches to similarly collecting the data. So that will be stuff that we will do, but also that we need to work with our demonstrator, the demonstrator sites to also develop. Yeah, that's our next step.
Okay, thank you very much for clarifying this. I don't know if there are any more questions from the audience. I guess not. So in that case, I was wondering regarding the environmental and economic impact, what criteria did you use to select the indicators? You mentioned that you reviewed some of the existing literature, but how did you specifically choose this criteria?
Thank you for the question. We have reviewed a number of possible indicators and proposed this set of the final list of the indicators based on the criteria such as its relevance and significance to the PEM impacts that occur in the PEM storage hydropower sector, as described in the international standards and guidelines, such as the guidelines from the International Hydropower Association, and also the availability of the data that we need for the analysis. So basically, those are the criteria that we use to select and propose these final lists of the indicators. But in practice, when we conduct the life cycle assessment, it is also possible to get the results for all possible indicators that are not even in our main focus, which is a part of our LCA process. But it would be overwhelming to present the results for all possible indicators in the story matrix. And this is also why we use some criteria that I mentioned and selected only a list of some indicators that we presented.
Okay, thank you very much for your answer. I guess that since there are no more questions from the audience, everything was very clear. So thank you once again to our speakers and to everyone who joined today. This workshop is part of STOR's broader mission to ensure that pumped storage hydropower remains at the heart of our resilient, sustainable, and flexible European energy system. And we look forward to continuing this conversation and sharing more results as the project progresses, since we haven't even turned a year old. So there's a lot to pay attention to. For that, don't forget to check out our website, story.eu, and social media profiles. I actually have prepared this slide. with the social media handles. So I'll let it here. Oh, sorry for this. Here are the social media handles. You can find us on LinkedIn and X, and we regularly post content about results and progress, as well as news from the project. So thank you once again for joining us today, and I wish you a good afternoon to everyone.